We'll be talking about banked curves in this question. So we have a situation where they're asking for the speed of a car as it goes around a banked curve. So the question says, at what speed will the car round a 52-meter radius curve go, banked at a 32-degree angle, if no friction is required between the road and the tires to prevent the car from slipping? So let's just break this question down. We're asked to solve for the speed, which is signified by a symbol called v. So that's what we're asked to solve. What are we given? Well, we're given the radius, which happens to be 52 meters, so that's our radius. And we do happen to have an angle. Because we're dealing with banked curves, keep in mind that banked curves are curves that are raised on one side and kept at ground level on the other side. So it produces this slanted curve, if you will. You see a lot of this in roller coasters. When roller coasters go down at a very fast velocity, and the first thing you'll see is a turn or a curve. It's very helpful to have a banked curve where it's at an angle, so that way the force is directed downwards. And you'll see a little bit about that as I draw the free body diagram. So a banked curve in general is basically a curve that is raised on one side and not raised on the other side, that produces this slanted look. And that's what you're seeing here. This drawing on the right, where it shows the car, we're looking at the car from behind. You'll see this car slanted at a angle of 32 degrees, as shown like right there. This is the bird's eye view of the curve, so the angle is in reference to here and here. And this car is actually right here on the banked curve. Okay, the first thing we should do, well, again, make sure you draw things out, just like I did here, so that way you have a better picture of what's going on. The first thing we should do is draw a free body diagram of this car as it goes around the curve. So here's the car. We're looking at it at eye level from the rear of the car, and we're going to label all the forces acting on this. So the forces that are acting on it is the weight, which goes downwards like this. So that is weight. We are also given the normal force, which goes like this. So it goes in that direction. Keep in mind the normal force always goes perpendicular to the surface. So you see how the normal force produces this perpendicular angle to the surface that it's on. That's what you're seeing right there. Okay, so this is my normal force. Actually, let me write it down. Let me write it like this. So this is my normal force. Okay. All right. There is no friction involved, so we're not going to have to worry about any forces going like this or like that. So we can actually focus more of our attention on the weight and the normal force. Now, if you were to look at the normal force in particular, you'll notice that it's going diagonally. It's going at an angle. Let me go ahead and actually show this to you in a more clear sense. So anything that goes at an angle like this, it has what we call a horizontal component and a vertical component. You'll notice that the normal force is obviously moving up, so that's signified by this line here. I'm going to draw it like this. Okay, so it is going upwards, but you notice it's also veering off to the left. Okay, it has some sort of leftwards motion to it. So I'm going to draw it like this. Okay, the upwards motion that you're seeing, that's our force normal y. This is the vertical component of the normal force, because the normal force does have some upwards motion. What you're seeing here is the horizontal motion of the normal force. We're going to label that as Fnx, our force normal x. That's what you're seeing right here in this situation. Okay? Let me actually write my force normal x down here so you can see it a little bit better. All right, so that's what you're seeing here. You'll notice that because this is a triangle, there's also an angle along with it. So I'm going to draw my angle right here. Okay, that angle is actually the same angle as this angle right here. So we have an angle of 32 degrees. Okay. All right, let's go ahead and continue on. Now, if you were to look at your weight and your Fny, you notice that your weight and Fny are going in equally opposite directions. The weight's going straight down. Your force normal with regard to the y-axis is going straight up. This goes to show that the force normal y is equivalent to my weight, whatever your weight would be. Okay? And your weight is equivalent to mass times gravity. So you can just, typically say that your force normal y is equivalent to mass times gravity. Okay? Now look at your force normal x. You notice that it's pointing towards the left. So if I were to look at the force normal x on my banked curve, the bird's eye view of the banked curve, you'll notice that your force normal x is actually going like this. It's pointing towards the center of the curve. It's pointing within the curve. If you were to look at the car at this point, you'll notice that the force normal is actually going, the force normal x, your horizontal normal force, is going this way. And if the car happens to go this way, your force normal x is directed this way. So you'll notice that the force normal x is directed towards the center. If I were to look here at the eye level view, we're looking at the car from behind, the center of the curve is like right here. Okay, this is the center of the curve. And if you were to look at your force normal x, isn't your force normal x pointing towards the center of the curve? And it turns out it does. So this goes to show that your force normal x is equivalent to the centripetal force. The centripetal force, the center-seeking force, also known as the centripetal force, is the horizontal normal force. It's the force that's responsible for keeping that car on the track. Without that force normal x, the horizontal normal force, the car would have just slid off the track really easily, and that would have been a bad thing. And so keep in mind that in a banked curve, the centripetal force is the horizontal normal force. All right, so now that we understand that, let's look into some of the trigonometry functions about that. I'm going to turn our attention over to the triangle here. And actually, let me go ahead and actually replicate that triangle really quick. So that way you can have a better sense of how that looks like. So I'm going to actually take that and redraw that in a blank space here so you can kind of see this a little bit better. Okay, so this right here, this is the force normal. Okay, so I'm going to label that as F sub n, and anything that goes at an angle has a horizontal component, which is signified with this vector right here going leftwards. This is my force normal x. And it's also going vertically upwards. You can see the normal force is actually also pointing upwards in addition to it pointing leftwards. So that's labeled like this. and we're going to label this as force normal y. Okay? Now keep in mind that your force normal x is equivalent to your centripetal force, and that your force normal y is equivalent to your weight. Okay? Because the force normal y is going upwards, the weight's going downwards, so there's your weight going downwards, and the two are said to be equal. And your force normal y, you can also break it down to this, mass times gravity. Going back to your force normal x, because your force normal x is your centripetal force, the centripetal force has its own equation. It's mv squared divided by r. Okay, so you might want to keep this into mind. Now let's go ahead and also label the sides of the triangle. This side right here is our normal force. We will label this as the hypotenuse. This side right here, the force normal x, also known as your centripetal force, just keep in mind the angle, 32, I forgot to tell you this, the angle in relation to the triangle here, our 32-degree angle is right at the bottom of that triangle, so I'm just going to write that down here, 32 degrees. Oops, let me just write that a little more cleanly. There we go. All right, now in relation to the angle, you'll notice that this side is on the opposite end of the triangle, so we're going to label this side as the opposite. And this side right here is actually touching the angle, so we're going to call this side the adjacent. Now, I'm looking at the force normal x and the force normal y. You notice that the force normal x is the opposite side, and the force normal y is the adjacent side. Now, I'm looking at the trigonometry functions. So if you are familiar with this, we're going to use the mnemonic SOHCAHTOA. And this is the sine equation, this is the cosine equation, and this is the tangent equation. If you notice, the force normal x and the force normal y gives us an opposite side and adjacent side. And we can actually put those two together by using the tangent equation. Tangent theta equals opposite over adjacent. Just a little recap. The first letter represents the trigonometry function with the angle. The second letter represents whatever in the numerator. The third letter represents whatever is in the denominator. Okay, all right, so now that we have our equation set, let's go ahead and do some substitutions. So tangent theta is the same thing as saying tangent of 32 because we're dealing with a 32-degree banked curve. Our opposite happens to be our force normal x. Okay? And our adjacent happens to be our force normal y. Well, let's substitute this even further. You'll notice that your force normal x is your centripetal force, showing right here. And your force normal y, that can be substituted by weight because force normal y equals the weight. So you can look at it like this now. Tangent 32 equals centripetal force divided by weight. And now we can actually break that down even further. Tangent of 32 equals the centripetal force. Well, centripetal force can be shown as mv squared over r. Okay, and your weight can also be substituted. I'm actually going to write this in a different color so you can see it. Weight can be broken down to its components, mass times gravity. So this right here, written in yellow, is the weight. And that's in the denominator because the weight's in the denominator. Now you have this equation. Tangent theta, let me just say theta instead of 32. We'll plug in the 32 a little bit later. Tangent theta is equivalent to mass times velocity squared divided by radius times mass times gravity. You'll notice that algebraically, the mass will cancel out. And what you've just have done was you've simplified the equation to this. Tangent theta equals velocity squared divided by radius times gravity. And what you've just put together is the equation for banked curves. This is the banked curve equation. This is something that you might need to keep in mind or remember. Okay? We're going to use this equation to solve for our question. So going back up to our question here, we are asked to solve for the velocity. We want to know how fast a car can go around a curve. And we also know that the curve has a 52-meter radius and a 32-degree angle. So we're going to go ahead and plug in our values here. Before we plug in the values, it's important to, let's just go ahead and rearrange the equation, because the equation is calling for the velocity. We're looking for the velocity. That means that the radius and the gravity has to be moved to the opposite sides. So let me just rewrite the equation really quick. Tangent theta equals velocity squared divided by radius times gravity. I'm going to move the radius and the gravity to the other side. So we're going to do that by multiplying both sides by radius times gravity. That cancels out, so our rearranged equation is velocity squared equals radius times gravity times tangent theta. Okay, once we're here, we can go ahead and plug in our values. So radius, go back again. So what was our radius again? Our radius was 52 meters. So 52 meters times our gravity, which is 9.80, times our tangent theta. And again, our theta is 32 degrees. And then once we're there, we can go ahead and solve it. So velocity squared equals this. So 52 times 9.80 times the tangent of 32. And you'll notice that you'll get an answer that's quite big, 318.433. It just keeps going. We're going to actually, well, you'll notice that that's not the final answer because your velocity happens to be squared. So that means we have to take the square root of that number in order to cancel out the square. So that way we're left with v. So taking the square root of that number gives me an answer of 17.844, which I'm going to roughly say 18 meters per second. So this is how fast the car should be going around that curve. Any number higher than that, the car is going to just slip off the curve, and that's not going to be a good thing. And so that is how to solve for a banked curve question.